Excuse me. Okay, so let's start. Right, so today I will cover all the forces. Newton's law, equilibrium forces, resultant force, and vectors, all that. And the next class, I will cover momentum, and the next class will go to energy and so on. Okay. Okay, so if you have any like subtopics, I feel like very confusing, you want me to cover, please let me know in through WhatsApp. Let me know in a direct message. Right, so we'll start. And let's start with the Newton's law first. Newton's laws and forces in equilibrium. Now, three laws. First law of inertia, right? Everything will, if it's moving, it will move, continue to move. If it's at rest, it will continue at rest, only if there is no external force. Newton's second law, force into is equal to mass times into acceleration, or we can say force is the rate of change of momentum, right? Actually, Newton's second law, we cannot say F equals to ma. That is the derivation of Newton's second law. Newton's second law is actually saying force is the rate of change of momentum. So to be very specific, you have to say rate of change of momentum instead of F equals to ma, because F equals to ma is the derivation, is the formula, is the quantification, that one. Okay. Now let's go to Newton's third law. I want to focus more on this third law today. Newton's third law, every action has equal and opposite reaction. This is a very general term. Now, if I see the layman terms, what's the meaning of this sentence? It says that in an interaction between two objects, the force applied by one object on the second one is equal to the force applied by the second on the first. And it is in exact opposite direction. This statement makes it very clear that we have two objects and the interaction between the two objects. Say that I have an object here, I hold it like this. The weight of the object pressed on my hand. So there's a force acting on my hand. There are two bodies, my hand and the object. To keep it at rest, I apply the same force upward. That is the same as in terms of magnitude, but opposite in direction. But that force that I apply is acting on the object. One is acting on my hand, one is acting on the object. Okay, say that we got two objects here. One ball is hitting another ball. The force produced by the first ball, let's say the first ball hits ball number 2, the force produced by first ball on the second ball, I label F1 on 2. Okay, so this is the force applied, and due to the rule of nature, every time you apply a force on one object, that object will apply the same force on the first object. So that is the first ball. So the second ball will apply the force on the first ball. That's F2 on 1. And these two forces, they are having the same line of action. Okay, opposite, but in the same, having the same magnitude. Now, similarly, I hold an object like this. The weight of the object presses on my hand. That force is acting on my hand. So that's force of object on hand. And then there's a reaction. Okay, the force that I apply on the object, that's force of my hand on the object. Similarly, when I punch the wall, okay, I apply the force on the wall, and the wall applied the same force on my fist, and then I feel the pain. I feel the pain is because of the reaction, not because of the force I apply on the wall, because that force is acting on the wall. the sensation I got is from the force that is acting on my feet, because there's two bodies here. Okay, there are two bodies here. So I feel the pain is because of the reaction force from the wall. Now, action and reaction pair. Action is the force acted by the first object. When I hit the wall, okay, my feet, that's the first object. I hit it, that's action force. Okay, so in this case, action would be F1 on F2, that's action. This one, the weight of the object is pressing my hand, so this is the action. This is the action force. Reaction is as a result of the object number 2 react, how it reacts to the first force. So this is my reaction force, R, reaction, and same, this is my reaction force. The force acting on my fist is the reaction force. Okay, so every action has a reaction. Just like when I want to move forward. If I want to move forward, I press the ground backward. I do not press the ground forward. If I press the ground forward with my foot, I'll be moving backwards. So if I want to move forward, then I press the ground with my foot backwards, and the ground presses me forward. So that's action and reaction pair. Okay, you see it everywhere. Okay, now why is this important? This is very important when it comes to analyzing the contact force between bodies. When you have multiple bodies, okay, you have to be very clear how many bodies you have and what are the forces acting on each and every one of them. Okay, for example, let's see one example here I have on the slide. Okay, here we got 3 bodies of the same mass. Cube 1, cube 2, and cube 3, and I apply a force of P from the left. A, write an expression for the acceleration of cube 3. B, write down expression for the resultant force on cube 3. C, write down expression for acceleration of cube 2. So we want to derive all the expressions, okay, for the contact force between these objects. And we need Newton's third law. All right, let's do this. Okay, the way we analyze this, guys, is you can analyze it like at once, looking at the whole diagram, or you can break it down into individual diagrams. Okay, if I want to analyze the contact force, let's say the question wants you to find what is the force of body number 2 acting on body number 3. How do I find that? Body number 2 acting on body number 3, meaning that that force is the contact between cube 2 and cube 3 is inside, right? How about if I want to find force of 3 on 2? What is the reaction force of body number 3 pressing on body number 2? All this, you need to use free body diagram. Okay, so now let me show you how to solve this. Let's say you apply a force of P acting on all these objects, and it will give them an acceleration. Okay, so this is not an equilibrium system, it is an unbalanced system, so there is acceleration. So let's say we have an acceleration A in the same direction as the net force. First, we derive the acceleration expression. F equals to ma, net force is P, assuming there's no frictional force. So P equals to m, I got 3 masses, so that would be 3m into acceleration. Acceleration equals to P divided by 3m. That's my acceleration. And one thing to note is that acceleration is the same for all bodies. In this case, because every single body, they are attached. So they are viewed as one single body, like one big body. So if mass 1 accelerate at 2 meters per second, then mass 2 and mass 3, they will accelerate at the same acceleration. Okay, so all of them, they have the same acceleration, which is P divided by 3m. Now m1, cube number 1, because I press m1, right? So m1 also presses m2. correct? So I label the force here, M1 press M2. What is this force? I call it F1 on 2. This force is acting on what body? Body number 2, not body number 1. Okay, body number 1 is the one applying, and the force is acting on body 2. And because of this force, Newton's third law, body number 2 exert the same force back on body number 1. So we have another force here, reaction force, F2 on 1. And we know that F1 on 2 is the same as F2 on 1. Okay, now same, M2. When I press M1, right? M1 press M2, M2 also press M3. So there's another force. This force, what do you call it? F2 on 3. This is the action again. Due to this action, there's a reaction. Body number 3 press back body number 2. So that's M3 on 2. Okay. Analyze the free body diagram. Now, I make M1 free from the system. That's why we call it free body diagram. So I make it alone, free from the system, and I only look at the forces acting on body number 1. F1 on 2, F2 on 3, they are not relevant. So which forces do I take? P is the one that acting on body 1, and F2 on 1 is also acting on body 1. So I put it in here. We have P, and then we have another force here, F2 on 1. And I know that this mass is accelerating, and an acceleration of P over 3m to the right. That's my first body diagram. Second body diagram for mass number 2, M2. What are the forces acting on body 2? We have F1 on 2. Okay, and then we also have F3 on 2. That is the reaction from cube number 3. So we have in this direction F3 on 2. And this body, same, it is accelerating at P over 3m to the right. And the last body, M3, there's one force only acting on 3, which is F2 on 3, because body number 3 behind it, there's no more object. Okay, so only one force, F2 on 3 acting on it, 2 on 3, and acceleration is P over 3m. Okay, after we have drawn all this free body diagram, then I use Newton's second law, analyze F equals to ma. Resultant force, this is F2 on 3 equals to m and then P over 3m. Cancel, cancel. So F2 on 3 is equals to P over 3. That is the magnitude of force applying on cube 3 by cube 2. Is P over 3. How about M2? F equals to ma. Again, because we got two forces here. So it's moving to the right, right? So this one should be bigger. I take the bigger, F1 on 2 minus F3 on 2 equals to ma. Okay, ma is P over 3. So this is P over 3. How about this one? 3 on 2. 2 on 3 is the same as 3 on 2, action reaction. So this one is also P over 3. F1 on 2 minus P over 3 equals to P over 3. So to find F1 on 2, that is 2 over 3 P. Last one, M1. F ma P minus F2 on 1 equals P over 3. F1 on 2 is the same as F2 on 1. So this is 2 over 3P from my answer here. Okay, so P minus 2 over 3P equals P over 3. And when you move this to the right, you'll find that you get P equals to P. So that satisfies the equation. So from my calculation, I have calculated that F1 on 2 is 2 over 3. F2 on 3 is this one. And that is the same for the opposite. F1 on 2, same as F2 on 1. Okay, so here, A, write an expression for the acceleration of cube 3. What is the acceleration of cube 3? Same, right, for all objects. So the acceleration is equals to P over 3m. Write down an expression for the resultant force on cube 3. Because every object, they have the same acceleration and they have the same mass. So if you use F equals to ma, they have the same resultant force. Okay, so expression for resultant force on cube 3, what is it? F equals to P over 3. Okay, P over 3, that is the resultant force. C, write down the expression for acceleration of cube 2. Same as your answer in A. A equals to P over 3m. D, write down an expression for resultant force on cube number 2. Same as your answer in B. Okay, all the blocks, they each have the same resultant force and acceleration. Now, comes to E and F. What is E? E, write an expression for force applied by cube 3 on cube 2. So this question is asking about the contact force. Cube 3 on cube 2, meaning that we want 3 on 2. And we know that it is the same as 2 on 3. What is my 2 on 3? This one. P over 3 is my expression, my answer. So P over 3. F, write an expression for force applied by cube 1 on 2. F1 on 2, same as F2 on 1. That's 2 over 3 P. That's my answer. Okay, so normally when we analyze free body diagram, we don't look at the contact force, right? Because the question did not ask about it. Sometimes when the question asks you, what is the contact force between these two? Then you have to analyze inside, okay? Draw the free body diagram. Because if you look at this as a whole, then meaning that this will cancel out. 1 and 2 cancel out with 2 on 1. 3 on 2 cancel out with 2 on 3. The net effect would be 0. But if you look at one individual object, then you have to take into account that contact force. Okay, so this is an example on finding the contact force between objects. Between objects. Okay, if you want to take a screenshot, you can take it down and I will erase this and I will go to the next section. Okay, next one. Newton's law and forces in equilibrium. Okay, so just now we talked about third law, right? Okay, let's see equilibrium and not equilibrium system. Suppose that I have an object, okay, a ball resting on the ground. Two bodies here, the ball and the ground, two bodies. Now, the weight of the ball presses on the ground. So here is F, ball on ground. And the ground presses it back. So we have F, ground on ball. Now, is it only these two forces? Is there any other forces? If I want to label everything out, then we still got two more forces. What forces are that? The forces from the field, gravitational field. So these two objects, they are in contact. They are called contact forces. The field does not require any contact. Okay, they call it field force. So if I label everything out, then we still have force acting on the ball. Okay, this is on the ball. What do we call this? Force of Earth, the gravity of Earth, okay, on the ball. And not only the ball, also on the ground. So the force of gravity, force of Earth on the ground. You have a total of 4 forces here. So if we have so many forces, then which one do we look at when we analyze whether a system, when we analyze a system, okay? What forces do we look at? Now, it depends on what you want to analyze. If you want to analyze the motion of the ball, let's say you want to see whether the ball is accelerating or at rest, then you only look at the forces acting on the ball. It has to be one body at a time. Okay, so if I want to analyze, let's say I want to know what is the motion, what is the effect of these forces acting on the ball, then you only see the force acting on the ball and do not see the forces acting on the ground. So which two I see? This one, F on ball, E on ball. So if I draw it here, we got F, G on ball, and we got another one, F, Earth on the ball. This one, irrelevant, on the ground, on the ground. Okay, so I only look at these two forces, and then I see, okay, if they are equal, then it's a balanced system. So this one, these forces, Earth on the ball, correspond to the mg, the weight of the ball. This one is the reaction. Okay, so normally when you draw free body diagram, you only draw R and mg, right? R and mg, R and mg. Okay, because that forces that you draw is only acting on that body. Okay, on other bodies, there are still many forces. Here. So if R same as mg, then no acceleration, the object will continue to do whatever it is, okay, doing initially. If it's falling, then it will continue to fall with constant velocity. If it's at rest, then it will continue to be at rest until there's an unbalanced force. How do we create an unbalanced force? Okay, so we have a system balance here. To create an unbalanced system, let's say I remove the ground. When I remove the ground, then what force disappear? You see, force of Earth on the ground disappear. Force of body on the ground, no more. Force of ground on body, this one is the reaction, right? The reaction from the ground, also no more. Only one force left when I remove the ground. That is the force of Earth on the body. That's the mg. So without the ground, then the only force acting on it is mg. Here you have a resultant force. So this would be unbalanced and it will fall at an acceleration of, you already know, g 9.81. Okay, similar to like we step on the ground. You see, since we were born, okay, we are always in contact with the ground. We are already so used to the feeling of being pressed by the ground. Everywhere we go, we are in contact with the ground. So we always feel our own weight. So we are so used to that feeling that if we leave the ground for a few seconds, we feel very strange. What is that strange feeling? The feeling of weightlessness, right? You feel it when you do bungee jump, you do free fall, you're in an elevator, you feel that, all that. And it is very strange feeling. Some people, they don't like it, right? Because we are so used to to feel the reaction. The weight that you feel, your own weight that you feel is actually the reaction. It is not the mg that you feel. So whatever change happened to your reaction affects the sensation that you get. Whatever change that happens to your mg do not affect the sensation because you are feeling the reaction. Because in some cases, your mg can stay the same, but the reaction can change, like in an elevator, right? So that's why you feel weightless and then you feel heavier sometimes when it accelerates upward. Okay, so that is the reaction force. Okay, we are feeling the reaction force. So here we got two systems, balanced and unbalanced system, right? Now, let me give you another example. Let's say we have a wall here. Okay, this is the wall. I put a spring here, okay, pressing on the wall, and then I compress the spring from the other end. Okay, now when I pressed it, I am applying a force, and it becomes an unbalanced system. So there's an acceleration towards the wall, and then as I compress, what happened to the spring? Spring and elastic material. This one we'll learn in the next few chapters. Elastic material, they have very unique properties that they can, in the molecular structure of elastic material, okay, this is the atoms of the elastic material. They want to maintain whichever distance that is best for them. If you try to disturb the distance, if you try to disturb the spacing between the molecules, let's say you pull it, and they will try to resist you. They will try to return to whichever distance that they want is best for them. So meaning that if you try to stretch, then it will return. If you try to compress the particles, then they will try to resist you. Okay, they will return. Meaning that the moment you apply the force on the elastic material, then a force is developed. The moment you apply, then a force inside the material is developed. And this force is not a constant force. It is a changing force. The more you press it, the greater the force becomes. So meaning that when you push the spring, what happened? Initially, there's acceleration, right? It is unbalanced system. So you push, and then the force inside the spring increases until one point you feel like it's very hard. You cannot push it any further. So at that state, at that instance, you have a balanced system. The force you apply is the same as the force in the string, and it's opposite. That is also a unbalanced system. Balanced system. Okay, so you can see for example, like pressure. What is our atmospheric pressure? Atmospheric pressure, 1 × 10⁵ Pascal. You learned this in previous secondary, right? So 1 × 10⁵. And then you have, what else? 76 cm/Hg. You have 1 atm. Now, this is different unit, right? What else? You got 15 psi. But we seldom use this, right? PSI. PSI stands for what? Pound per square inch.
Square.
Yes. Pound per square inch, 15 pounds. Meaning that, imagine you take one tiny boxes, like 1 square inch surface area. Okay? And then you extend this to the edge of the atmosphere, up there, all the way to the edge of the atmosphere. You get a column of air, right? You get a column of air. This column of air weighs 15 pounds. That is the meaning of this atmospheric pressure. So meaning that every 1 square inch, there's 15 pounds of air sitting on top of it, pressing it. So if you lie down on the ground, then what is your surface area of your body? 15 pounds, 15 pounds, 15 pounds, 15 pounds, 15 pounds, all that's add up. All this add up, it becomes a very huge amount of force acting on you. But the question is, how come you don't feel it? Why? Because, you see, because fluid, right? Fluid can be gases, can be liquid, right? So in this case, it's gases. Fluid, they have a very unique property, is that they apply force in every direction, right? You learn this in pressure of liquids, they apply in every direction. So meaning that if you have many 15 pounds pressing on you, then you have the same amount of 15 pounds pressing from your feet up. These two forces, they cancel out. You have 15 pounds, many 15 pounds pressing from the left. You have the same number of 15 pounds pressing from the right. These two forces, they cancel out. Everywhere, every direction, they cancel out. So you don't feel the atmospheric pressure. It's because of this fluid property that pressure acts in everywhere. That is a balanced system. That is also a balanced system. Okay, no matter how large is the force, you can give 1 million newtons. 1 million Newton here, 1 million Newton here, we don't feel the effect. There's no effect. Okay, no matter how large the force, they all cancel out each other. So in a balanced system, when you have an object here, force in this direction, and force in this direction, force in this direction, force in this direction, they cancel out algebraically. When I add it up, the algebraic sum, what does that mean by algebraic sum? Meaning that we add it with the sign. If this is positive, this opposite with it is negative. This is positive, this opposite with it is negative. The algebraic sum is 0. This is a balanced system. Okay, so a balanced system has no acceleration, is at rest. Okay, it's already proven with the example in your real life. Okay, now here we look at one typical example of the exam questions. Here we have a string hanging an object. Okay, what are the forces acting? Okay, so we have mg, this is on the ball, and we have tension, right? Tension. Tension is developed in the string. This is the last molecule of the string. This is the second last molecule. Okay, imagine like this. This is the molecule, the last one, meaning that below this molecule is the ball. Okay, so this is the last molecule, second last. When you hang the ball, then you are trying to pull the molecule away from the second one. What happened to elastic material? They want to maintain, return to original position. So when you pull it down, then they resist by returning. So the force is developed inside, and this force is called the tension, right? The tension, how do we label tension? We label upward because this molecule is trying to come back. So the tension we label up, meaning that it is going out of the object. If you pull it from the side, then the tension will be to the right, opposite to the object. Okay, so that's why we label tension here, T up and mg down. And in this case, T is the same as mg, right? Balance. Now, imagine, let's say now this ball is charged, positively charged. And then I bring a positive plate, put it at the side. So there's an electric field, and positive repel positive. This electric field will create an electric force, Fe, to the right. So what happened is that at this moment, momentarily, there's a net force acting to the right, and it will create acceleration. This ball will accelerate to the right. And as the ball accelerates to the right, what is the change that happened to the tension? The tension initially is vertical down, right? So as it moves to the right, then the tension slowly, it is making an angle with the vertical. Let's call it alpha. Okay, so it is making an angle with the vertical, meaning that when there's unbalanced force acting on the system, that system adjusts itself to compensate the change. When the ball is here, then it remains at rest. So here it returns back to equilibrium. Okay, so the unbalanced condition only happen momentarily, and very quickly it comes back to equilibrium. When the ball is at this position, what forces you have? Okay, let's see. We got mg down, we got Fe, right? Fe, and then we got tension in this direction. You see, we got mg and Fe, meaning that if you only look at these two forces, then the ball should come down here. This is the resultant effect of mg and Fe. But the ball did not come down here. The ball tries to come down. It tries to come down, but it is not allowed because the string is hanging it, because the string will not break. Okay, so we have three forces, T, mg, and Fe. All these three forces, the overall effect is a balance. How do I draw the vector diagram? The vector diagram, you need to know how to draw it because often they will ask you. Okay, to draw the vector diagram, remember, we only take the forces out from the system. We don't want to draw it on that diagram, on the original diagram. Whatever is a diagram given here, we don't want it. We draw a new diagram. Okay, so we draw a new diagram, find some space where you have enough space to draw. We're going to start with any one of it. Let's say I take the mg. Now, when you draw, imagine that you pick and place. Okay, pick and place, meaning that I don't change it. I don't pick and I don't rotate, I don't place. No, I pick and place. I don't change the direction. So mg is straight down. Mg. And then when I add to Fe, Fe is to the right, right? So I pick up Fe, I place it. Where do I place it? Now I'm here. I started here, I go here, and I continue from here. So I pick it and I place it over here. So don't draw your Fe like this. Suddenly sloping already. No, it's not in the same direction. Initially, it is pointing at east. This is now northeast. No, change back. Okay, so your vector should be like this, Fe. Now, currently I'm here. I add one more. There are three vectors. So T, I add it. Now, where should I draw it? Do I join it all the way here or do I stop it halfway? That depends on the system. If it's an equilibrium system, then the vector diagram, it is a closed loop. Remember this. If it's an equilibrium system, your vector diagram is a closed loop. Okay, so arrow down, go here, come back to the starting position. This vector diagram shows that this system is equilibrium because for equilibrium system, the summation of vector, meaning that when I add the vector, actually now I'm doing the summation. When I draw the diagram, then I'm doing the summation. I'm adding the vector is 0. The summation of vector is 0. In some cases, you will not get a closed loop. Okay, in that case, it is not a equilibrium system. For example, if there's no T, let's say there's no T, only two forces, mg and Fe. How do I draw the vector diagram? I got two vector, right? Okay, pick it up, place, mg. Pick the Fe, place, Fe. Is there any other vector? No more. There's no T. There's only two vector. Is it a closed triangle? No.
No.
So if it's not a closed triangle, then it is not equilibrium. And if it's not equilibrium, there is resultant force. How do I draw the resultant force? Starting here, draw to the end, put double arrow. This is Fr. What is the difference between diagram number 2 and diagram number 1? Diagram number 1, there is no resultant force. This one got, and you can see the arrow. This arrow, they are all pointing in line with each other. Okay, not even one arrow is going against one another one. This arrow, this is going against this two because this is the resultant. Okay, so two diagram, very different diagram. First one, equilibrium. Second one, unbalanced, not equilibrium. Okay, yeah. So from now on, whenever you draw vector diagram, remember, we don't want the original diagram. We take out the vector, draw a new one. Take out a vector, draw a new one. And then when it comes to analyzing, you first need to know your vector diagram before you even analyze. So this becomes very important. If your vector diagram is wrong, then all your analysis is wrong. Okay. OI. Right. If you want to take down, you can take down, and then I erase it. I'll go to the next slide. Okay, let's look at one more example of equilibrium system. Also a very typical one, the inclined plane. Okay, so here we have a sloping surface, alpha here. Okay. Mg, first we label the force. Mg straight down. Now, depends on what is your reference axis. Okay, your Cartesian axis. For inclined plane, I will take the Cartesian plane like this, meaning that the x-axis, I change it, make it parallel to the slope, and the y-axis, I make it perpendicular to the slope. Okay, so if I take this reference, that means the Mg is not my horizontal, neither my vertical, because it is not parallel to any of the axes. It's not parallel to the y, it's not parallel to the x. So meaning that I need to resolve the Mg. Okay, so if I take, let's say I take like conventional Cartesian like this, straight, then I don't need to resolve my Mg because it's already parallel to the y. That's the vertical component. Okay, but I will have trouble with other forces. Okay, so that's why I take the sloping one, especially the R and the friction, all that. Okay, I take this reference, and then this angle here. What is this angle? This angle is the same as angle over here, is alpha. Okay, why is it the same? Very simple mathematics, you can prove it like this. You have one line, line 1. Another line, line 2. Let's say I draw a normal. Okay, I draw a normal to line 1. Call this N1. This line is normal, perpendicular to line 1. And then I draw another normal to line 2. Let's call this N2. Okay, I got two lines and two normal. They are normals. If the two line is making an angle gamma, then the angle between their normal will be the same. This is also gamma. Okay, I repeat. If the angle between the two lines is gamma, then the angle between their normals will also be the same. That's why here is same. This one, alpha, this one, alpha. Okay, you can think of this base as line 1 and the slope is line 2. The N1, what is my N1? My N1 is the mg line. If I extend the mg, this is my N1. And my N2 is the y-axis. This is my N2. Okay, line 1, line 2, N1, N2. That's why the angle here is the same as the incline angle. Whatever is the angle of incline, it is the same as the angle between mg and the y-axis. Okay, so from here, I resolve the mg. In this direction, this is mg sine alpha. And this direction is mg cos alpha. This mg cos alpha is asking the block to come here, but it is not allowed because it is pressing on the surface. So the surface will press it back in this direction. Thus you get the reaction. Also Newton's third law. And then the mg sine alpha is bringing it down in this direction. That depends whether there is frictional force or not. Okay, let's just say there's no frictional force. So the resultant force acting on this object would be mg sine alpha in this direction. Okay, so F equals to ma. F is mg sine alpha, taking the horizontal, meaning that anything that is parallel to x-axis. And remember, x-axis, now my x-axis is sloping, not horizontal, it's sloping. Okay, so anything parallel to this is horizontal component. Mg sine alpha equals to m acceleration. So acceleration equals to mg sine alpha divided by m. Cancel out the m, I get g sine alpha. You see this expression, acceleration depends on the g and the alpha. What happens if I increase the steepness? Meaning that if I increase the steepness, the alpha increase. Here we have sine alpha. What is your sine graph? Sine graph is like a wave, right? Like this. Sine graph. What is the maximum angle I can increase? Let's start with this. Okay, I increase the slope, increase until straight 90. I can go beyond that. Okay, so maximum I can do is 90. Meaning that from this sine graph, I only look at until 90. The first quarter of the graph. So anything behind is not needed. So look at this first quarter of the graph is rising. When you increase the degree, the alpha, the value gets closer to 1. Right? So sine graph, the amplitude is 1 and minus 1. When you increase the alpha, angle increase, then this sine alpha approaches 1. When it is 90 degree straight, this is become 1. So meaning that A equals to G, then it will be falling vertically. Okay, so when alpha increases, when you increase the slope, the steepness, the acceleration will increase. Acceleration in which direction? Same as the resultant force. If your resultant force is here, then your acceleration is also here, sliding down. That's your acceleration. Okay. Now, what if there is a friction? If there's a friction, the way we label it along the surface, F, the horizontal component. So if there's a friction, then we use F equals to MA, mg sine alpha minus the friction equals to MA. Okay, so if friction is less than the forward force, okay, the mg sine theta, if it's less than it, then still it will accelerate downward. Example, if alpha is 10, mass is 10 kg, F is 10 Newton. Put in the formula, okay, we get 10, 9.81, sine 10 minus 10 and 10a. Do simple calculation, find a, you get 0.70 ms minus 2. Still, there is acceleration. If the friction is the same as the mg sine theta, equals to mg sine theta, what do you get? Then this would be in equilibrium, meaning that it will be at rest, or it can slide down with constant velocity. This one have to remember, because many students forgot the second one. Rest, okay. If it's at rest, then obvious it's equilibrium. Sometimes the question says it is sliding down with constant velocity. Okay, then you have to know also it is equilibrium also. Okay, meaning that the horizontal, they are balanced. Vertical also balanced. Okay, so if that's F equals to mg. So I can write my equation mg sine alpha equals to F. That's for the horizontal, and then vertical R equals to mg cos x. Here I get my equation 1, I get my equation 2. I can solve it simultaneously. If you want to find any of the forces, R, F, mg, or the friction. Okay, now for equilibrium, don't forget, not only the forces, moment also has to be balanced. So the total moment has to be 0. What happens if forces are balanced, moment is not balanced? That is a couple. That is a couple, torque, right? So moment has to be balanced, force also, then you get the equilibrium. Then we can very straight away we can see the moment, because all these forces is acting at the center of the object, right? Okay, at the center here. So we can assume that this object is small enough that all the forces approaches the center. So if I take moment at the center, then all the forces is acting on that point. The total moment is 0. Total moment 0, total forces balance. This is a balanced system. Okay, so now we are going to take 3-minute break, and then we'll come back and continue. Okay, so 3-minute break. I will see you guys back in 8. Now it's 57, so 8. Okay, guys, we continue. Huh? Okay, so far we talk about equilibrium system and contact forces. So now we analyze equilibrium system. Okay, especially in finding the forces. So if you're not sure how to do, then pay attention here. So T1, T2, and 7. We got 3 vector here, 3 forces. Let's say that this is equilibrium. Okay, so the effect of all of these 3 forces is rest, equilibrium. So I know that the vector summation of these 3 is 0, right? Now, there are 2 ways I can solve this. If a question asks you to find what is T1 and what is T2, 2 ways you can solve it. And you need to know how, both ways, because sometimes the question will ask you to use method 1, sometimes they'll ask you to use method 2. Okay, so method 1 is vector summation. So vector summation is like drawing the triangle, okay, drawing the triangle. And when you draw the triangle, before you even draw it, you should know that this is a closed triangle because it's equilibrium. Now be careful, not all force systems is equilibrium, okay? So you have to know what is the system, is it equilibrium or not? If it's not equilibrium, then you cannot get a closed triangle. So to draw it, vector diagram, again, I start, pick and place, pick the 7. Now I'm not going to use this diagram. I will draw a new diagram. So pick, place. This is 7.0 Newton. Be careful with the angle. I pick T2. Place, join to the tip. So T2 is over here. Let me use a different color. T2. T2. Angle here, 50. Okay, if I extend line of action of the 7 Newton, 50 with T2. So that's 50. Then I join to T1. T1 should join all the way back, starting position, T1. What is the angle here? You can draw a parallel line on this side. Okay, this line is parallel to T1. Because parallel, they are the same vector. Okay, what is the angle here? I want the angle here. T1 and T2. Again, I use this 35 plus 9 plus 50, 85. So I have something like this. 2 parallel lines. This is the transversal. Here is 85. So here would be 95. Okay, they both add up to 180. So meaning that here is 95. Okay, 50, 95, here, 35. After you have drawn the vector diagram, then you can solve it. Find T1 and T2. How do I solve it? I can solve it because this is not a right angle, right? So if it's a right angle, you can just use Pythagoras theorem or the Sochatua. But if you don't get a right angle triangle, you get something like this, then you have to solve it using the cosine and sine rule. Okay, cosine rule and sine rule. So in this case, you can just use the sine rule. Okay, because you have all the angles given. So the sine rule, how do I use it? First, I find T1. T1 over, this is the sine I want to find, right? So I look at the opposite angle. This sine opposite angle is 50. So I sine the angle 50. Equals to, I cannot take T2 because if I take T2, then I got 2 unknowns. So I take 7.0 divided by, what is the opposite angle? 95. So that's sine 95. So I solve for T1. 7 divided by sine 95 times sine 50. Okay, I get 5.3827 blah blah blah. Dot dot dot. Many significant figures. So how many should I take? Look at the question. If the question two significant figure, okay, 7.0, that's two significant figure. Then I take 2. This one approaches 5.4 Newton. That's my answer. T2 over opposite angle is 35. So sine 35 equals to 7 sine 95. Okay. T2 equals to 4.03. Again, two significant figure, so T2 approaches 4.0 Newton. Solving using vectors. Second, solving using resolution of forces. When I solve using resolution of forces, before I resolve, pick your reference axis. I'm going to take conventional Cartesian system as my reference axis. So X, Y. Now, again, I'm not going to use its diagram. I'm drawing a new one. Draw the Cartesian plane, Y, X, and then I put the forces in. T2, 50, and T1, 35. And then we have mg 7.0 here. Any vector that is parallel to the axis, they are either the horizontal or the vertical. So T1 and T2, they are not. So we have to resolve them. Resolve these two forces, 7.0 and this one no need to resolve. It's already the vertical. So resolve these two, I get T1 sine 35 up T1 cos 35, T2 cos 50, T2 sine 50, and then 7.0 Newton. Resolve everything, then you know left-right balance, up-down balance, only if this is a balanced system, equilibrium. So T1, use a different color. T1 sine 35, same as T2 sine 50. Equation 1. Up, down, so same, you add up. This one add up with this one equal to the opposite one. So T1 cos 35 plus T2 cos 50 equals to 7. That's equation 2. Solve simultaneously, and then you can get the answer. Okay, I write it here on the bottom left. T1 equals to T2 6. Okay, that's equation 3. Sub 3 into 2, so I get cos 35 plus T2 cos 50 equals to 7.0. It's simplifying. I'm going to get 1.094 T2 plus T2 equals to 7. Okay, so T2 equals to 4.0, same answer. Sub back into 1, oh no, sub back into 3, and you get T1 equals to 5.4 Newton.
Alright.
Okay. So two methods. Anyone you can use. Anyone. If they do not specify. So if you have 3 or more forces, you solve it the same way. But if you have more forces, like 4, then the vector summation becomes very difficult because you cannot get a triangle. You have one more vector, you get a quadrilateral. So it's best if you have many forces, you solve it using the resolution. If you've only got 2 or 3, then you can solve it using the triangle, the vector summation. And remember, if the system is not balanced, you cannot write this. They are not equal if they are not equilibrium. Okay, in some cases, you are given a force system and you are asked to find the resultant force. Okay, like finding the resultant force from this force systems. So that is an example of unbalanced system. Okay, we are going to look at a few examples, 1 or 2 examples of that after this. Okay, if you want to take this down, you can take it down. I erase this and I go to the next slide. Okay, one example like this. Let's say we have okay, let's say we have a equilibrium system here. The beam is hinged at one point. So this is like a pin support, meaning that it can rotate, it cannot translate. And then point B, we got tension, we got weight, 2 forces. So let's say the question says that it is at rest. So if it's at rest, then you know it is balanced, right? So balance meaning that the vector diagram should be what? Should be a closed triangle. Now, but here on diagram, only 2 forces are shown, T and W. If only 2 forces, you cannot get a triangle, you cannot get a closed loop. There must be 3 minimum. So where is the third force? Okay, it's not shown here, but you have to know because we have a support here. If you remember from our last lesson in moment, if you have a support, then you have a reaction. Okay, so the reaction is acting at this support. Now, here, if I extend the line of action of this force, it touches at this point, let's call it P. The reaction, I know that reaction plus the T plus the W should be a closed loop, right? So, but where is the reaction pointing at? Is it like here, here, or should it be horizontal? Okay, so you have to look at the moment also. That's why not only you see it from the force perspective, you also have to analyze the moment, meaning that the reaction has to be a reaction that will not cause a net moment on the system. For example, okay, here the weight is coming from this point P, and then the tension also crosses this point P. So the reaction has to be also pointing at this point P. Why? So that if I take moment at point P, the net effect is 0. Because moment about P, all these 3 forces, the W, the R, the T, they point, the line of action crosses the point. Okay, so if you have a point here, the forces acting on the point, the turning effect is 0. So when I take moment about P, then the moment total is 0. If the reaction were pointing in other direction, for example, if it's pointing like here, okay, if it's pointing, let's say, in this direction. Then when I calculate the moment, let's say I analyze moment, I take moment about point P. What will be my moment? T has no turning effect, W has no turning effect, but the R here creates a turning effect. So what happened? It's not balanced. My analysis doesn't make sense. Okay, so for this to be equilibrium, the total moment has to be the same also. That's why the reaction has to be pointing at the P. If the question asks you this, why it has to be pointing at the B, at the P? Because total moment must be the same as well. So from here, you can analyze from force, okay, using forces. I can draw the closed diagram. This is W. Pick and place W. Pick up the R, place over here, R. And the T, like this. Forces balance, no resultant force. Also, moment, sum of moment about P is 0. That means no rotation. And here, no translation. That's equilibrium. Okay. If they give you angle, let's say here alpha, here gamma. Okay. So taking moment at any point, equilibrium, remember in an equilibrium system, moment at any point is 0, total moment. So if I take moment, let's say moment at point A, at the hinge, moment at point A. What is the moment? This force, the reaction has no turning effect because it's pointing at point A. The line of action is on point A. Okay, no, the point A is on the line of action, so it has no turning effect. So only the W and the T. So moment about A, this W is clockwise. This T is anti-clockwise. So T sine gamma. Okay, I resolve it vertically, would be equals to, okay, times the distance, right? So we don't know the distance. Let's just say we put it in ratio. Okay, this is 2, 2, 2. Okay, let's do it like this. Distance from A to B is A to B is D, and from A to W is 2/3. Okay, 2/3. So T sine theta times into the distance D. Okay, that's A to B. Equal W times into 2/3 of D. Okay. So moment about A is also balanced. You take moment at point B, same. Moment at point B, then the tension would have no turning effect. And you have to calculate the reaction and the W. This one I can. So 3T sine sig gamma equals to 2W. Okay, now I want you guys to try this. Let's say we have a force 40 Newton, 50 Newton, separated by angle 55. Is this equilibrium? No, because you got two vectors. You add up, you cannot get a closed triangle. So it's not like equilibrium. Meaning that if it's not equilibrium, then it has a resultant force, right? Now, you need to find what is the magnitude and direction of the resultant force. Okay, you try it now. I'll give you a few minutes and then I will talk about the answers. Okay, remember I said got two methods, right? Two methods you can use. First is the summation of vector, means you draw triangles. Second is the resolution. Now be careful when you use the resolution, you have to know the angle, meaning that when I draw the axis like this, what is the angle here? What is the angle here? I'm not sure. It may or it may not be symmetry. Okay, meaning that these two forces, they may or may not be symmetry, meaning that you can't just divide the 55 by 2. It could be like this, right? Okay. So to solve this, right, you can use the vector summation. If I give you the angle here, like I say, this is like 35 and this is 25, then no problem, you can solve it. Resolution. Because you know what is the angle of this force. What is the angle of this force? Every single force, the angle respect to the Cartesian, you know, you can solve it using resolution. Okay, now let's say I'm going to solve it using a vector. So draw a vector diagram. Okay, find the magnitude and direction and draw the vector diagram. Okay, a few minutes. If you got the answer, let me know. Yes. 80 Newton, 30.8 degree to the force 40. The rest can do. If you cannot do, let me know. If you need explanation. Okay, your vector. Okay, angle, we use sine rule to find it. And then after you got this, right, every time you get the answer, you draw it again on the original diagram. Okay, show it on the original. So I draw something like this. $80 Newton, and then label the angle. For vector questions, always show your vector diagram. It helps with the marks. I'm talking about in the exam, in the international exam, your final exam. Okay, always show diagram. Okay, so guys, I will send you the exercise past years on forces. Okay, so all about forces. Quite a lot, 25 pages. Okay, so if you can finish it, then you it's better lah. You do more, then you become better. Okay, I'll send the forces to you. It's like all the force questions from many years of past years sorted out into one document. So you got many questions here, 25 pages. Okay, so yeah, we still got a bit of time. You can take the time and do it. If you have any questions, including the previous exercises, okay, you can take the time. Let me know. And for the force exercise, if you can finish it, you do all. If you cannot, then you do as many as you can. Okay, you do as many as you can. Yeah, how was the exam, by the way? Insufficient time. Oh, I insufficient time. Is it uh easy, medium, hard? Okay, okay. Medium. Must do rectilinear motion and rectification. Yes. Okay. What is the chapter you guys are learning now? Is it moment?
Moment.
Moment. Okay. All right, guys. If you want to go, you can go, and we'll continue next week. Right, bye. Yeah.